So this is going to be chapter 1, and we're going to start with the lecture. Now, I do tend to leave some stuff into my PowerPoints and put some of this stuff in my PowerPoints that maybe you'll end up skipping and kind of ignoring. You should start seeing the PowerPoints uploaded and attached. My upload speed is super slow for some reason. Not sure what's going on this week. But it is going. It is going. So this will be chapter 1. And you'll see these sort of like learning objectives things. They're probably not super important for you, but it does tell you where, like, if you go in this lecture and go, oh, Dr. Clausen, I don't remember ever talking about this. These are where those are. So like 1.9 at chapter 1.9 is where you get things like distinguishing between heat and temperature. So they're kind of useful just to leave in. Hopefully they help you out someday. If they don't, that's okay. You can just sort of ignore it. Okay. So the science for all seasons, this is what's one of the ways people like to talk about chemistry. Chemistry is the study of matter and its changes. Everything we do involves chemistry. Everything we are is chemistry, at least physically, maybe not spiritually. Everything around us is chemistry. So you all have, this is one of those things about chemistry that's kind of interesting. It's that people live in chemistry every day of their lives. We all do all the time. And so we actually know a lot of chemistry. Every time you've cooked, it's been chemistry. Every time you've shopped, it's been chemistry. That thing that rotted on you in your fridge, that's chemistry. It's all chemistry. So you know actually a tremendous amount of chemistry because all the stuff you've needed to know to stay alive to this point is chemistry. But that chemistry, you've never probably thought about it expressly. You've never probably really concentrated on why exactly did that happen, and perhaps never used the scientific method on that specific topic. And so what you're going to find is I'm going to talk about things in an express manner because it's a science and chemistry. If you really start thinking about it, and I'll try to do my job for giving you examples that will help you connect these things, you already kind of knew that. You just maybe never thought about it expressly. So please, if you got that sense coming into this class of chemistry, oh my goodness, this is going to be hard, this is going to be terrible, etc., etc., please just take a step back for a second and go, it's just everything around me all the time. I already know almost all of this. I just really haven't thought about it expressly and put numbers to it before. But now I get to see how that works. Okay, so science and technology. Science is the process of seeking an understanding of underlying principles of nature. It's going to involve two facets typically. We have the technological, which would be what's usually referred to as factual, or the philosophical, which would be the theoretical. Now, this is not necessarily the only way you could do this definition, nor this division. You could also say technological is the developmental, where you make things. Philosophical is the underpinnings, where you understand things. It's not necessarily always theoretical that's in philosophical. It can be things that are experimental that sort of build up that underlying knowledge base so that you could then try to predict the next steps for your technological developments. And vice versa. Technological developments help to inform and allow you to make new philosophical discoveries. So they're not a division that is a divide, that is a chasm. It's a division of a cycle where one feeds into the next. Technology is going to be the direct application of knowledge to solve problems. Science actually grew out of natural philosophy, and that's why like a PhD is a doctor of philosophy, is because originally it was natural philosophy. Or another way of saying that is philosophical speculation about nature, though it doesn't necessarily have to be speculation only. It's just that The Greek tradition was heavily speculative and actually testing your theories. And the Greek tradition was considered something meaning you did not have any conviction in the theory you're putting forward. And so it was considered bad to test things. However, many similar systems actually grew out of a multitude of different cultures. There's cultures of philosophical, natural philosophers in South America. There was ones in North America. There was ones in Africa, of course. There was ones in Asia. Asia's are kind of amazing because it's like a 6,000-year history of natural philosophy, which is just wild. Chemistry is the discipline of science that's going to deal with the behavior of matter. That's not actually the only thing that happens with chemistry. Chemistry actually also heavily involved in the behavior of light, which is not matter. But most of chemistry is matter, and most of the things you would care about for chemistry is matter. So it's actually a really, really fair definition. That does a pretty good job, actually. Let me see if I can get this. There we go. That's weird then. And take first. Okay, so the Barsonian dream and Carsonian nightmare. So it is the dream of Francis Bacon, which is a philosopher, that science would solve the world's problems and enrich human life with new inventions, thereby increasing happiness and prosperity. And to be fair to Francis Bacon, his dream in many, many ways did come true. Of course, not in every way, as we know living in this world that we live in. But the average person in today's world, the poorest person in a developed country, lives a life that a 9th century emperor could only dream of. Okay? The literally everything in material possession wise in your life is just heads and tails above the possible things that a 9th century emperor could ever get their hands on. The things they would do to get like cooling on a hot summer day, right? Or be able to get ice in every drink if you wanted to. Just wild. Rachel Carson, this is a biologist, published Silent Spring in 1962. She proposed that the use of chemicals to control insects threatened the destruction of all life. And there is some pretty strong evidence that, while not necessarily the destruction of all life, it definitely has extremely adverse effects to the environment and adverse effects to us humans in the environment and all the other animals in that environment. Green chemistry is going to use materials and processes that are intended to prevent or reduce pollution at its source. Sustainable chemistry is designed to meet the needs of the present generation without compromising the needs of future generations. Two incredibly cool developments. They've taken a tremendous amount of effort over the last about, only been really seriously pursued in maybe the last 50 years or so. But the progress that has been made in making things less damaging to the environment, less resource intensive, reducing the energy costs, have, despite the failure of many policy decisions and many other decisions that have been made, have actually reduced the consumption of each person considerably on this planet. Even with the growing population, we actually are more efficient in many of the countries that have been doing these developments than we were back when we had populations that were only half or even a third the size. So it's actually been making incredible progress. This has been really, really, really turning things around very quickly. But it's only been something that's really been seriously pursued for probably about 30 years now. It was sort of like the beginnings back in the 80s. So science has 5 characteristics. Science is testable, reproducible, explanatory, predictive, and tentative. We're going to talk a bit about the scientific method and these characteristics of science. But I know that oftentimes when I start on the scientific method and these characteristics of science, many people of faith kind of start tuning out and going science and faith, they're mutually exclusive. Please know that science and faith are two things that just aren't really mixed at all, okay? The basis of science is the ability to test things. And so the faith in and of itself requires no testing. And you can't live your life completely through science because you don't have the time to test everything. That just wouldn't be possible. By the time you'd even begin even 10% of the testing you need on any given field, things have already spun completely out of control. I'm gonna try not going into it because it becomes some of an emotional thing. But COVID is a pretty good example of this. By the time that they could even begin to test the COVID virus, it was everywhere. It was that was done. So you just can't live your life completely within science, and some things you're just going to have to go, I have faith and I'm going to move forward. Doesn't have to be a faith in religion, doesn't have to be a faith in anything. I'm just saying that you have to have faith in your convictions on what you're going to move forward on. Okay? So hopefully I did that well. And you understand that science and faith are not mutually exclusive things. They do not actually, are not counter to each other in any way whatsoever. Scientific hypotheses are going to be testable explanations of observed data. These hypotheses are going to be tested by designing and performing experiments. In fact, it is not a hypothesis if it cannot be tested. And so this is really where the, for example, people always want to try to ask questions like, is there a God? Or is there aliens, like UFOs? And these aren't really scientific questions because you can't actually ever disprove them, right? There is no test that you could do to disprove them. And so they are not scientific hypotheses at all. And science really doesn't have a place in that. It's just not something you can test. So remember that whenever you're coming up with a scientific hypothesis, it has to be able to be disproved. Okay? Because that's what your experiments are ultimately going to be able to do. I don't know how much logic courses anybody's had, or like the philosophy of logic, or argumentation. If you get any of those courses, one of the things you'll learn in those is the same thing I'm going to tell you right now, which is that you can't actually ever prove anything. Okay? What you can do is you can disprove everything else, try to disprove the thing that is left. You fail to disprove the thing that's left, and then you can begrudgingly go, I guess I have to do it, just, take that. And then you try to disprove it a few more times, and you fail. And then if you're a scientist, you just keep doing that forever. And eventually someday you disprove it, and then you have to come up with a whole new hypothesis. No, some things you just don't ever disprove, and those are going to be what's left. And those will be the things that we base all of our scientific understandings on. So scientific laws, these are a bit different than the scientific method. So scientific laws are going to summarize large amounts of scientific data. They're going to provide descriptions of natural phenomena. Things like the law of gravity, the law of conservation of mass and matter, etc. Many of the scientific laws can be stated mathematically. This is very important actually, like Boyle's law. Is PV equals K, a constant. And what that means is that PV are actually related to each other. So for example, how a fridge works is you can use a compressor in a fridge, and this compressor is actually going to change the temperature. Typically, many compressors actually use a volume change to do this pressure change. You can actually prove this to yourself if you ever want to, because you can take a balloon, of course, and you can blow into it, and or you can take a balloon that's already filled and you can put pressure to the sides and the volume shrinks, right? And so that would actually be proving Boyle's law, by the way. The thing about a scientific law is This is an accurate definition of it, but one of the things it kind of misses is that scientific laws are also something that either mathematically must be true, because every single observation we've ever seen all follow this mathematically perfectly, or they have to be something you can observe over and over and over and over every moment of your life. So everyone all the time is observing the law of gravity. And so the law of gravity is being tested literally constantly, all the time. The law of conservation of mass, or matter, is being tested all the time by everyone on the planet, always. And so these things are constantly tested, and they have to be true because they've been tested so many times it's uncountable. Scientific theory is going to be a set of tested hypotheses. These are going to explain natural phenomena. Scientific theories are going to be the best current explanation for a natural phenomenon that has not currently been disproven. Theories are always tentative. They may change as observations of nature change, and they should. And many people kind of think that like modern day knowledge has all the answers and these theories are perfect, but they're not. For example, the Big Bang Theory actually had one of its key tenets that was sort of propping it up. It only had two, by the way, which actually isn't very good. But it actually had one of those partially disproven. And so the Big Bang Theory is probably not quite right. There's probably some other stuff that needs to go in that. The other big one that kind of got changed recently was about 2 years ago. An undergraduate was listening to a lecture, went up to their professor and went, you know, Professor, you talked about metals and why metals are metals, and wouldn't it be easier to do it this way? And the professor was listening, which is great. Really cool conversation then. And that's good college. And at good college, students should teach the professor a little bit. The professor should teach the students a little bit, and we all learn something. And so the professor went, why don't we? And actually tried it. And so they actually, it doesn't matter to most people. Honestly, it really won't matter to probably 99% of people on the planet. But a little bit of what the definition for a metal is changed 2 years ago. So the exact definition of a metal actually changed, which is pretty crazy if you think about it. So scientific models, these are going to be tangible items or pictures that are used to represent invisible processes. For example, we're going to use this model when we start talking about how like liquids and vapors work. And this is a basic molecular model, okay? And it's a pretty good model, and it works very well. So you'll actually see a lot of this. Models will present them almost as facts, but know that ultimately models are scientific theories, and they're just something that has been tested over and over, and we haven't disproven them yet. But scientific models have been disproven in the past, and not that long ago. So very likely there are some models that are not perfect. Molecular modeling, so molecules are going to be groups of two or more atoms that are held together by chemical bonds. Molecular models are going to be three-dimensional representations of these molecules. And we use these because we actually did manage to take a picture of a molecule just recently. That did happen. But it's so expensive and it's so time-consuming that when it comes down to thinking about molecules and what matter's made of, we have to use models and we have to use abstractions. They're just so different than how you think of the world around you. Kind of like if anybody's ever looked like at a really close zoom up of a diamond or metals, it doesn't look anything like the metal you were wearing on your finger or your earring or is made of your desk, is made out of. It doesn't look anything like that when you get really, really close. And so there's lots of different abstractions that are used. And we'll show a few of those and you'll get some idea of what these things look like. and how they act. But understand that, yes, it just is the world we live in as human beings and we see as human beings is colored heavily by our perceptions. And the actual world that exists around us is significantly different than that. It's not, we definitely are not getting the world as it exists in our brains. So, the limitations of science. So science is limited to studying that which is observable, as well as processes in which variables can be controlled. This is a decent statement. In the past, that was definitely true. And in general, the order of easiness, the ability to actually prove that something is wrong and be able to have a model withstands these tests is greatly aided by being able to reduce the variables that go into it. However, our ability to not control every variable has progressively improved as we get more knowledge of what systems look like. And so, for example, observable is not necessarily the observable you think of as like a normal layperson. It can be a bit more abstract than that. So, for example, observable can mean that we can interact with, okay, in some way. And so these processes, typically we do need to control some variables because if we have too many variables, it becomes impossible to solve. But with the ability to rapidly test things, especially with computers have just opened the world for science. We can test a lot more variables now than we used to. It used to be if you left 10 variables uncontrolled, it would be unsolvable. You'd have to have teams of hundreds of scientists trying to run calculations every day, 12 hours a day for years and years. That's why, rockets in the 1960s were such a huge endeavor. But computers allow you to take variables and fit multiple variables much faster, do thousands of tests a day if you want on some systems so that we can fit these variables better. So science and technology, the risks and benefits. Science and technology are going to be interrelated. They're going to involve both risks and benefits like any activity in the world does. Every single activity can be broken down into risks and benefits. Risk-benefit analysis is going to involve an estimate called the desirability quotient. This is the DQ, which is the benefits over risks. I get this question quite often when I have in-person lectures, and it has to do with the COVID, specifically like the lab leak theory, which is that they were engineering a type of coronavirus in the Wuhan labs, and that then escaped. And they were actually engineering a type of virus in the labs that would be very consistent with the virus that ended up being spread throughout the planet. And then the real question becomes, and the one that typically why I bring this up here is that, yes, this is exactly the sort of calculation that you would want to do for these things. And considering there are 14 viruses that would kill off 90% of the planet in existence today, that have been developed by humans in government projects by both the United States and the USSR. This risk-benefit desirability quotient has not always been done. On the other hand, the other way of that, nuclear power is a great example of where this desirability quotient has been done, and then people just threw it out the window and just said, no nuclear, I don't care what the risk-benefit reward is. And now we're kind of suffering for that decision, but because nuclear power would have fixed the entire idea of global warming, would never have been a thing with the nuclear power being widespread, of course. But anyways, yeah, so it's an incredibly important decision that we use. These are some more closer to home things that you can use it for. So for example, if we take all causes, then your lifetime risk of dying from it is 100%. Nobody gets out of this alive, right? We all end up dying eventually. So 100%, 1 out of 1. Gonna die. If we take cigarettes, your lifetime risk ends up being about 25%. That's 1 pack a day. Cigarettes really are a huge risk, not a whole lot of benefit compared to the risk. Heart disease, on the other hand, huge risk if you start living long enough. Cancer, also huge risk if you start living long enough. And so these are the risks that you would experience. And you can use those risks to sort of figure out, is it worth 15 minutes a day of running or 15 minutes a day of cardiovascular activity of any type, doesn't have to be running, that would reduce my heart disease by from 0.2 to 0.05. Is that worthwhile? Yeah, probably. I myself am guilty of not always doing a great job of that. But yes, I fully express that the fact that I really should do a better job of that. Cancers, again, there are things you can do to reduce your risk of cancers, and are those activities. Some of them are not. So for example, motor vehicles is a 0.01, so 1/100 would be deaths in motor vehicle accidents. I think it's well worth that risk to get into a motor vehicle to save me the time, the half a day every day it would take me to get to and from my workplace, right? If I were to try to walk. So, very worthwhile. Is it a risk being in a home? Yes, probably. Your risk from home accidents is going to be vastly lower than your risk from death through exposure. Natural forces is pretty low risk, though if you're in certain places, the risk goes up, right? So you'd want to be a little bit more careful. There are places that the risk, lifetime odds are sometimes applied by people, but they really are not actually applicable. So for example, peanut butter aflatoxin, this is not actually a risk for most people. This is more of a risk that you would want to take into account if your situation would be applicable to that. And like terrorist attack, it's not a real risk for most people, but for people that are going to be in certain positions in life, that is a greater risk. These can get a bit complicated when you get into the more abstract ones, the ones that have really, really low numbers of the overall population. So chemistry is typically called the central science, and that's kind of because chemistry takes that place in the middle, where all the other sciences typically interrelate through chemistry. And that's because chemistry is just an incredibly broad and old science. It's that science that handles all the molecules, and all the molecules make everything up, and everything being made up of molecules means that it's all chemistry to some degree, but we don't need to know every single aspect of chemistry to be a great botanist, for example, or to do the greatest agricultural production ever done. We don't need to know all of chemistry, but you need to know a little. So for example, agriculture, you need to know a little bit about fertilizers, you need to know a little bit about fuels, you need to know a little bit about growing conditions, temperatures, biomarkers, where it's a good place to grow. Maybe you don't know the exact name of each thing, but you need to know enough to be able to use it, right? And then medicine is really closely tied to chemistry these days. It's funny because medicine is actually closer tied to chemistry than it is biology now. More tested for chemistry than biology. So let's talk a bit about solving society's problems through scientific research. We have applied research. This can involve a study of a specific problem in industry or the environment. So for example, here we have George Washington Carver. Um, I'm not going to go too far into his history and all the stuff he did and everything. I'm just going to barely even begin to scratch the surface of him. But if you ever want an individual that's very worthwhile looking up and looking into their history, he is one of those individuals. Very, very interesting person. Very cool. Really prolific. So George Washington Carver worked with peanuts. It's an example of applied research. In his research, he actually developed more than 300 products from peanuts. And yeah, so that's George Washington Carver. This is a basic research person. This involves the search for knowledge for its own sake. The findings of basic research may someday be applied to specific problems in industry or environment, but doesn't necessarily always have a specific problem right now that it could be applied to. And so, for example, Gertrude Ellion's work with purines and their role in the cell is an example of basic research. And it's an example of research that was basic research like 20, 30 years ago. No, more. That's more than 20, 30 years ago now. My goodness. It's like 40, 50 years ago. Wow. I guess I'm living in the past. But now there is tremendous numbers of new biochemistry experiments that have been done. There is new works in various different enzyme blockers for things like HIV, etc., that have been able to be synthesized and made partially due to her work. Okay, so this is an example of where basic research tends to find its way into applied research overall. There is, of course, some basic research that never quite makes its way into applied research, but you kind of have to do that and take that with the basic research that becomes fundamental of our way of life, because you don't know which one's going to be which. So you just try to learn what you can about the world around you, and then apply it where you can. Chemistry is going to be the study of matter and its changes. Matter is going to be anything that has mass and volume. So let's talk a bit about mass and weight. So mass is going to be the measure of the amount of matter in an object. Weight is going to be the measure of the gravitational force on that matter that's in that object. So for example, you've all probably seen like the moon landing or astronauts in the space station, and their mass didn't change. Well, at least in short term. Their mass doesn't change in short term. And so their mass on Earth, their mass up on the space station, their mass on the moon, in the short term it didn't change. It's the exact same or very close to. The weight, on the other hand, changed tremendously. And that's because on Earth we have the Earth's gravity pulling us down onto the Earth. When we get up into a space station, because of how that orbits around the planet, we're always in free fall, and so we don't experience most of the effects of gravity when we're on the space station. And so that weight then greatly is reduced, and that's why you see the astronauts floating around and having fun with, the water floating around, little beads and stuff. And again, on the moon, similar thing. They're jumping around like that on the moon because the weight is greatly reduced, and that's because the moon has a lot less of a gravitational well, is what that's called. A lot less gravitational force pulling things down. So physical properties are going to be those properties of a substance that can be observed without changing the substance. So some of the examples of physical property are going to be things like color, the mass, the weight. They can also be things like how malleable it is. Here we have copper, right? We can bend that. And that's a physical property of copper. We could cut the copper. And again, that's another physical property. The shape is a physical property. These are physical properties. So these are some more physical properties. We have temperature, of course, 0 degrees Celsius for ice water, 100 degrees Celsius for boiling water. Those are both physical properties. The melting point and boiling point of water. Mass, so a nickel weight is about 5 grams. A penny weighs about 2.5 grams. And so those would be the mass, and those would again be physical properties. It doesn't change the characteristics, the fundamental compound of it. Color, so sulfur is going to be yellow, bromine is reddish brown, and again, this doesn't change from sulfur to carbon because it's yellow or because of the color necessarily. Taste, acids or sours, bases are bitter. Odor, benzyl acetate smells like jasmine, hydrogen sulfide smells like rotten eggs. And so the odor is actually involved with hydrogen sulfide. That is the marker for rotting, actually. And that's why rotten eggs smell rotten. And like if you turn on a gas tap and you let it go, it smells kind of rotten because they actually add hydrogen sulfide to that usually. So boiling point, hardness, density, these are all physical properties. By the way, density oftentimes used to determine whether something is gold or not. It's one of the original tests, so that's kind of an interesting use of density and physical properties. Chemical properties. These are going to be those properties of a substance that can only be studied by forming a new substance. So, for example, if you have, say, carbon, and you burn carbon, that's going to be a chemical change. You're testing the chemical properties of the carbon, that it burns very well. Which is what people noticed when they got coal. They burned it, and they went, hey, this burns really well. And so what's produced from that is actually you combine carbon with oxygen, that produces carbon dioxide and water, usually. Or if it's just pure carbon, just carbon dioxide. Iron, you all know some chemical properties of iron. Iron rusts, and so when it combines with oxygen, it makes iron oxide, which is rust. Silver tarnishes, and so that's actually the combination with sulfur, in case you're wondering. And that's silver sulfide. That's that sort of tarnish, in case you don't remember, is that sort of like black, almost plaque-looking thing that happens on silver substances like jewelry or silverware. Nitroglycerin, this explodes. This actually is decomposing to produce a mixture of gases when nitroglycerin goes off. That's TNT, by the way, is nitroglycerin in a matrix that holds it in place, so it doesn't explode quite as easy. Pure nitroglycerin, by the way, would explode from a heavy impact. That's why like old TNT will actually blow up if you hit it too hard, and it's sweat. That if you ever see TNT that's sweating, or any of the explosives that have like little oil on the surface, don't handle them. Please get a bomb disposal unit. I want my students alive and happy. Carbon monoxide. This is toxic. It combines with hemoglobin actually, and it'll cause anoxia. It'll actually cause you to suffocate despite the fact that you're still breathing, because it'll combine with what carries your oxygen in your blood. And so this is actually one of the leading causes of death around a house where chemicals are actually involved, is carbon monoxide. And that's why you should always have a carbon monoxide alarm in case you ever have any gas flames in your house. Neon, this is inert, does not react with anything, overall anything. Extremely hard to get a reaction with neon. So physical changes are going to be changes in which the chemical identity of a substance is not changed. So some of these examples will be the melting and the freezing that we had looked at before. These are physical changes. Physical changes can be really simple. You could tear something, you could cut something, and again, the identity of it, for example, if I tear paper, it doesn't change from being paper all of a sudden. It's still paper. It's just two pieces of paper, right? If I melt water, it's still water. If I freeze water, it's still water. If I boil water, it's still water. It's just water vapor, right? And later on, it can come back as liquid water. So let's talk about the classifications of matter a little bit. So a solid has a definite shape and volume. A liquid has a definite volume, but no definite shape. A gas has neither definite volume nor definite shape. And you already kind of knew this. So like your desk, that's a solid. It has a definite shape, a definite volume. And you know, it doesn't really change that much. You can bend it maybe a little bit here and there. But you know, the shape is pretty much staying what it is most of the time. A liquid is going to have a definite volume, but no definite shape. So like my water here, it fills the cup on the bottom, it fills in all the spaces on the bottom, but it doesn't pop out the top on me without me doing something stupid. Which I actually did in this lecture, so whoops. Anyways, so definite shape, definite volume, but no definite shape, right? It's not going to fill the entire room. A gas, on the other hand, has no definite volume, no definite shape. There's no shape to a gas. It's just going to fill the entire room. It'll fill any space it can get to until it stops being able to leave. So these are different examples of the states of matter. And here you can see a solid, a liquid, and a gas. Another way of thinking about this, by the way, is solids have rigid connections between the molecules or atoms they're made of. Liquids have about 80% of those connections broken and only have 20% of the connections remaining. So they're kind of like if you've ever had something bust off your car or your bike or something and flop around a lot. It's a bit like that, but a bunch of that. And gas is going to have no real connections between any of these individual particles. They're just all going to bounce around everywhere, and so they fill the whole space because they bounce off each other and bounce all over the place. So this is the overall flow chart for matter with nice pretty pictures. This is probably one of the coolest things about this book is the pictures are fantastic, really cool, and how they incorporate them into their various different diagrams and helping you understand. So probably the neatest part about the book, actually. And so here we have all matter. It can be broken down into substances and mixtures. Under substances, there's elements. And those are the things on the periodic table. You can't purify those anymore. You can't subdivide those anymore without going into like subatomic particles. So for example, that would be like oxygen, carbon, lithium, gold. All of these things are elements. Those are those things that are listed on the periodic table. This right here would be compounds. They're going to be some combination of elements that will make a compound. Literally, compound meaning a compounding of things. Homogeneous or heterogeneous. These are the two different types of mixtures. And so a mixture is going to be where you have mixed various different substances together and they are no longer pure. But they have not chemically changed. These are going to be physical changes. You're only going to mix them together. So if you started off with gold and silver, I guess, since gold and silver is over here. If you took gold, you took silver, you mixed it, you'd get a mixture. If it is homogeneous or homogeneous, depending on which side of the Atlantic you're on, you won't be able to tell any difference of any specific part from the overall mixture. For example, if you look at any part of this, they all look the same, and that's because this is a homogeneous mixture. Over here we have a heterogeneous mixture because this part, you can tell the difference between that part and that part. And that means that they're different genius. So heterogeneous, if you're on the other side of the Atlantic, by the way, that would be heterogeneous. And this is homogeneous. This is very different than compounds, by the way. Notice that you still have gold, you still have silver. If you were to melt these, you could actually separate them. On the other hand, compounds, you would no longer have those individual elements as individual elements. They would be combined into compounds, and they're bound much more tightly. They'll require chemical changes to do anything to. And they're due to chemical changes. So again, elements composed of one type of atom. Atoms are going to be your smallest particle of an element. Atom literally means indivisible, but it is actually visible. You can you can subdivide atoms. It was a misunderstanding back in the day, but we kept the name because it's a great name. Atoms. So again, elements will be represented by chemical symbols. Some of these examples will be things like chlorine, hydrogen, magnesium. Compounds are going to be made of two or more elements. They're going to be chemically combined. Some examples are going to be sodium chloride, like table salt, water, H2O. My formula kind of got messed up here. This should be a subscript. I'm going to have to go back through and fix these again. They keep changing the... Microsoft keeps doing all this stuff to justify their $30 billion they spent on AI, and it is causing me havoc. So, one day I will catch up with them. But for now, this should have been a subscript too, so H2O. Sorry about that. And this right here is sugar. And so, for example, it has 6 carbons, 12 hydrogens, 6 oxygens. That makes a sugar molecule. So many of these compounds are going to exist as groups of atoms bonded together as a unit. These units would be then called molecules. Let me make sure I point something out here, which, man, I don't know what it is, but it is just not as widely known or understood as you would expect. For example, Greenpeace, one of the largest environmental action groups in the world, for over a decade had a deal on their website that said the carbon dioxide that comes off of a plant, the carbon dioxide that comes off of a human, and the carbon dioxide that comes off of a car are different things, and that the one that comes off of a car is poisonous while the carbon dioxide off the plant is beneficial. This isn't true. Compounds are compounds. So compounds, and carbon dioxide is 1 carbon, 2 oxygens. It's a compound. Anytime you have a combination of CO2, 1 carbon, 2 oxygens, that is carbon dioxide. They all have the exact same properties. It doesn't matter. They can be in different mixtures. And so some of these different things actually do have different mixtures. Though, funny enough, the carbon dioxide mixture that comes off of a typical human would actually be more harmful to your breath than a properly running car. Properly running being the key word there. A lot of not properly running cars. But anyways, that's beside the point. Carbon monoxide, no matter where it's sourced, has the exact same properties, same chemical properties, equally contributes to global warming, not different. So, wherever you get the compound from, there's not a huge difference between them, okay? They're going to have the same chemical properties, same physical properties overall. Not a huge difference. I mean, there's no difference at all. That'll be meaningful. So, mixtures. There's going to be a mixture. There's going to be a physical blend of 2 or more substances. Homogeneous mixtures are uniform in composition, and so you can't see any individual part that's different. And that's where the homogeneous name comes from. Homo meaning same. Heterogeneous, on the other hand, is going to have a non-uniform composition. So you're going to be able to look at a heterogeneous mixture, and you'll be able to see different parts of it. And so hetero then again meaning different. So the 7 SI base units are these right here. Here we have length, and that's denoted by the meter. Here we have mass, that's the kilogram. Here we have time, which is the second. Temperature, which is Kelvin. The amount of a substance, and that's measured in moles. The electric current is ampere. You've probably actually seen this. It's on every plug for every device you ever bought. Which is either AMP or just capital A, depending. The luminous intensity is candela, CD. If you actually look at a lot of light bulbs, they'll have this number on them. They also have, there's 2 other standards for numbers that are used sometimes for the luminosity or the luminous intensity. However, candela is the SI unit. Sometimes it doesn't get used though, because it's actually a pretty small one, because it would be the light one candle gives off, so that's not a whole lot of light. Kelvin, by the way, is kind of interesting. You probably were thinking temperature, and you were thinking either Fahrenheit or Celsius, degrees Fahrenheit, degrees Celsius. The degree symbol in degrees Fahrenheit and degrees Celsius is actually because they're relative measurements. So we arbitrarily decided a 0 for those. The 0 degrees Celsius is actually the freezing point of water, but it's not really a meaningful number. It's arbitrary because it changes depending on where you are. And so Kelvin, on the other hand, is actually an absolute 0 number. There is an absolute 0 that is a constant throughout this universe. And so that's why there's no degree here. And it's never written with a degree. Because, again, like all these other ones, these are all absolute scales. And they can be measured from a fundamental, anywhere in the universe you could measure these. So these are some of the numeric prefixes that you can find, and you can then use to modify these different units. Okay. Now you kind of know a number of these prefixes already, and that's probably from like computers mostly. So most people know things like a terabyte, gigabyte, megabyte, kilobyte. And those are kind of the ones that most people would have heard of and know. And these are actually the symbols. So for example, TB, terabyte, the T was always tera. And that actually always stood for it being 10 to the 12th, or a million times a million, in case you're wondering, bytes, which is a measurement of data, or processing actually. So giga, that's a billion, 10 to the 9th. Mega, that one's 10 to the 6th. That's denoted by the large M. These are all large ones, by the way, and then we get into small ones starting right here, which is the kilo. Now, everybody knows the kilo. It's 1,000 of something, and they know that because, like, if I'm going to go, I want 50K, what am I saying? I'm saying I want 50 kilo dollars. K meaning kilo, thousands. I want a, okay, I'm going to use a terrible example. Hopefully I don't get in trouble with this one. I want a kilo of Coke. I want a kilogram of Coke, right? Which is 1,000 grams. It's a terrible example. Why that was the one that came up to my mind, I have no idea. Anyways, maybe I watched a movie or something recently. So hecto, this would be 100 of something. Deca, not to be confused with deci, which is like decimal, right? Deca is 10 of something. Deci is like decimal, 1/10 of things. Or you could say decimeter, which is 1/10 of something. Another way of representing 1 over 10, by the way, would be to represent it as 10 to the negative 1. That means the same thing. The negative sign means it's in the denominator, so you're dividing it by it. And then this number right here means that's the number of times you would multiply the tens. And so, for example, 10 to the negative 1, 1 over 10. 10 to the negative 2, 1 over 100, which is what we're seeing right here for the decimal equivalent. By the way, that's centi, easy to remember because of century or centipede. So 1/100th. Milli, or like millipede, millennium, is 1 over 1,000. Micro, like microprocessor, like microbiology. These microliter, I don't know if you guys have ever heard of microliter. Anyways, this is 1/1,000,000th of something. The symbol for micro, by the way, is actually, this looks like a U here, but it's actually called mu. Okay? Yeah, like Mewtwo. Pokemon. And yes, what you'll see is you'll oftentimes see this as a basically cursive U because many word processors and stuff, it becomes very difficult to do a mu symbol in them. You can also represent micro, by the way, by putting MC. So, for example, you could put micrometers, MCM. MC for the micro, small m for a meter. And by the way, microbiology, processors, these are all measured in micrometers, which is why they're called microbiology or microprocessor. Nanoparticles or nanomachines measured in nanometers, and that is 10 to the negative ninth or a 1 billionth of a meter. Very, 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 very small. Pico, on the other hand, this would be the sort of measurements you do things like, well, actually, the newest processors have started doing things in like pico and femto meter increments. And it gets really crazy at this scale because this is small enough where electrons can kind of pop in and out of existence on you and just bypass physical barriers. So you get some really crazy behaviors when you start getting down to pico and femto time scales or distance scales. Femtoseconds starts getting really crazy too. So anyways, they're kind of neat. 10 to the negative 12th is pico. 10 to the negative 15th is femto. So let's talk a bit about the measurements of matter. For the SI unit, the base measurement of mass is actually the kilogram. This is kind of unusual because all the other ones don't have prefixes. It's only the kilogram that typically is done with a prefix, and this is historically important. So the kilogram used to be a literal mass that they kept in a vault, and then if they needed to make a really precise measurement and try to figure out an offset of it or make a new one, they would then bring out the literal kilogram, which was an object, that they would then measure against that other thing, and then that thing would be so many grams above or below a kilogram. It's no longer a physical object, thank goodness. They actually damaged the original kilogram. Luckily, they had some offset ones that were a little bit, they knew the difference of, and so they could, recreate it. But the original kilogram did actually get damaged. If they had never made copies to back that up, they would have actually changed the kilogram. So, way. Quite crazy. Quite wild. The length, this is the SI base unit of length, is going to be the meter. The volume, the SI unit of volume is actually the cubic meter. This one's kind of weird. There's very little, if anything, that's actually done in cubic meters in the world, period. It's just not widely used. It's a pretty big number, actually, because if you measure out a meter, it's larger than your shoulder width by a pretty good amount. So if you put your hands, not quite all the way out, but pretty close, that's a meter, and you make a cube out of that. So it's actually a pretty big measurement. It'd be like one of those big balls they throw around at concerts and stuff. So it's a pretty big measurement. You sometimes see stuff like in the atmosphere measuring it, but it doesn't get used a lot. The time, this is the second. We all use the second all the time, so that one's cool. By the way, you will notice that the SI units are different than the metric units. There is a small amount of difference, though the metric units are much closer to the SI units than the imperial, which is what the people in the United States use. And funny enough, in case anybody was wondering why we don't do the metric, officially we are supposed to have adopted the metric system. By treaty, we were supposed to have done that in the 1980s. So we are only not quite 40 years past due. Not quite. Not that it really matters, to be honest. Everything has conversions in the United States on them, so it doesn't really matter. Nano world. So nanotechnology is the study of manipulating matter at the atomic or molecular level, because that's nanometer level. And you can do some really pretty cool stuff. This is a carbon nanotube. They're quite a bit stronger than steel, and as far as that structure. Density, this is defined as the amount of matter in a given amount of space. So, for example, density would equal the mass over the volume. And so, for example, here's the density of copper. So we have a 1 centimeter cube on each side. By the way, that would be a milliliter, or a cc, or a centimeter cubed would be its volume. The weight then would be 8.94. And so the density would be 8.94 grams over a cc, a milliliter, or a centimeter cubed. In this case, we use centimeter cubed. To calculate the density of a metal sample with a mass of 18.96 grams and a volume of 4.31 centimeters to the cubed. I forgot to make it so it hides until... Ah, man. All my PowerPoints got rid of all their formatting stuff. That's weird. Or not all of it, I guess. Some of it remained. Alright. That must have been when I saved them into the new drive. Anyways. Not that particularly matters, because I guess you could have paused it at the beginning, but I guess... anyways. It is good once we get to problems like this if you go ahead and pause these. And I'll try to hide these from the future. I'm sorry that I didn't realize that that my hiding got stripped. So if you pause these when I first bring up the problem, it's a really, really good practice to just go ahead and try to work the problem yourself and see where you get, what you end up with. And then go on to how I solve the problem, because ultimately me solving problems on video is only going to do so much for you. What's really going to let you exceed and excel and actually get valuable things from this course is you doing the problems and then slowly fixing any issues that are popping up. Okay? So that's just a better way to do it. You get more from the lecture. Anyways, so we're going to use the formula here. Density equals mass over volume. To be honest, you don't actually need a formula as long as you know density is grams over centimeters cubed. And the reason that is because if you use dimensional analysis, which is just a fancy way of saying, hey, units are variables, okay? So if you use these units here, you can actually always get the correct answer. So let me go ahead and show you this. Here we have this 18.96 grams, and let me step back for a second and talk a bit about basic problem solving. So I'm going to take this opportunity to drop a sort of truth of the world on you, like one of the most valuable pieces of advice you could ever actually apply to your life. It sounds so simple, so stupid, that you're probably going to ignore me here. And I'm going to probably present this to you in the least convincing way because I'm a chemistry person. Not a motivational speaker. But all problems that can be solved can be moved towards being solved by a simple formula. Okay? And this simple formula is simply, what do I have? What do I need? And then how do I get there? Okay? Sounds really simple. Sounds like something you already knew. And yes, you did. But if you express these things in a way such as writing them down and then working through each of these steps, you can come up with much better plans of how to solve simple math problems, but how to solve like even major issues, okay? And it's one of those things that they do studies repeatedly all the time, every few years. They've been doing them for 40-something, 50 years now. And every single time they find out that people that do this, that express, where am I at right now? What do I want to achieve in the future? And then how can I do that? In every problem, if they just do that for any major problem, their success rate just skyrockets. It becomes ridiculously uncomparable. Something like an 80% improvement in success rate. Just fantastic. So, I know, you didn't expect a life lesson in chemistry, but hopefully it helps you out. And it really is valuable. I wish I did it more in my own life. But I kind of came late to that realization myself. So, anyways, what do I have? Well, I have these two numbers, don't I? I have 18.96 grams, so I have a grams. I have 4.31 centimeters cubed. What do I need? I need a density. What is density? Well, density is grams over centimeters cubed, as you can see in the previous slide. And as you can see in this slide as well, because I revealed the answer by accident. But if you then take, well, I have 18.96 grams, right? I want grams per centimeter cubed. I have another number that is centimeters cubed right here. So what would happen if I put this number over this one? Remember, these units are part of this number, so they always should stay together. They are one thing. This lacks meaning without the grams. This lacks context without the 18.96. They are one thing. It's much like saying 18.96x. X just being a measurement of the universe we call grams. Okay? It's a variable. And so right here we have the 4.31 centimeters cubed. We take the 18.69 grams, we divide that by 4.31 centimeters cubed. My division works like this. I do one of the slashes because I have to write on one line, and using the equation editor is extremely time consuming, and I just don't have time to do that. I'm sorry. You may want to draw it out with a line like that on the bottom, and then put the 4.31 centimeters cubed. Eventually I have a little tablet that I'll sync up with this computer, and I'll do that. I won't be able to do it tonight though, because I did not bring it with me, and I forgot. Once I do the math, 18.96 divided by 4.31, that's going to give me 4.40, and it's going to be grams per centimeter cubed. And again, this is a division symbol, just the same as a line under would have been. It's just when I write it out in text, that's what it looks like. Okay, so let's talk a bit about energy. So heat and temperature. Energy is going to be the ability to change matter, either physically or chemically. Energy is going to exist in two major forms. We have potential energy. This is going to be stored energy. It is energy that is potential, that has not actually been used yet. Okay? This is energy in the fuel that hasn't been consumed. This is energy in the battery that hasn't been used up yet. Kinetic energy, on the other hand, is the energy in motion. It is you moving your arm, you throwing something, the car in motion. It is the energy being expressed. So heat, this is energy that is transferred from hotter objects to cooler objects. Actually a pretty dang good definition. Not circular, does a good job. One of the cool things about this book, it actually does a really good job of giving simple definitions that are also correct, which is really unusual for science textbooks. Temperature, this is the average kinetic energy of the atoms or molecules that make up an object. The best way to think about temperature is if you have a single object moving, you could calculate the kinetic energy. If you had two objects moving in the opposite directions and they collide, if they had the same kinetic energy, they would stop each other and they'd cancel out. And so what ends up happening if I have 1 million objects I have to calculate the kinetic energy for? Or if I have 1 billion or 10 to the 23rd objects I have to calculate? Well, it becomes impossible. They're going in too many directions. They have too many different kinetic energies. It just is a mess. And so what we do is we have temperature. Temperature is just a measure of the average randomized kinetic energy in a system. Okay? And so it's just a measure of all the kinetic energy of all the particles in a system, and they're all kind of going all over the place. So randomized chaotic kinetic energy. That's probably your best way of thinking of it. So units of heat. Heat energy is often going to be measured in calories or joules. 1 calorie is going to be the amount of heat required to change the temperature of 1 gram of water to 1 degree Celsius. So you'd raise it 1 degree Celsius for 1 gram of water. Please note that this is the lowercase c. When you see the capital C calorie, that's actually a kilocalorie. That's what's on the back of the labels for your food. Okay? Those are the food labels. A calorie is going to be 4.184 joules. And so that same amount of energy would raise 1 gram of water, 1 degree Celsius. That's 4.184 joules, or 1 calorie would do those. That's the same amount of energy. They're inequality. They're same. A food calorie, capital C again, it's the capitalized one. This is actually a kilocalorie. I was not involved in that decision, and I probably would not have made that same decision. But they did, and so it is. These are the temperature scales. So this right here is Celsius. I find Celsius the easiest to deal with. And that is 0 degrees Celsius, the freezing point of water. 100 degrees Celsius is the boiling point of water. On the other hand, Kelvin. Kelvin has the same differences per Kelvin. So 1 Kelvin difference is 1 degree Celsius difference. Going up 100 degrees Celsius would be going up 100 Kelvin. But the starting points are different. And that's because the 0 for Celsius is the freezing point of water. The 0 for Kelvin is what's referred to as absolute zero. And what that is that means there is no randomized kinetic energy at all. Okay? Everything is either frozen in place or they are all moving in the exact same direction with no real variance in their speeds. Okay? So either there's not randomized kinetic energy in that system anymore. Fahrenheit, on the other hand, is a completely different scale. 32 degrees Fahrenheit is the freezing point of water. That's why your car goes ding at 34, actually, is because you'll start seeing ice, because it's close to 32. And the boiling point of water is 212 degrees. By the way, that's one of the reasons why if you ever look at cooking things, they're always telling you, like, go up to a near 200 degrees. Because that's boiling point of water, it's going to kill everything. So you won't have anything to make you sick in it. Not that you can't still get sick even if you cook something really through. If it was rotten before, you could still get sick. But it greatly reduces your chances of getting sick. So that's a 180 degree difference, by the way. If you ever need to calculate between Celsius and Fahrenheit, it's actually one of the easier ways to deal with that. Is just to remember 32 degrees is 0 degrees Celsius. And so any number you get out in the Fahrenheit is always 32 degrees higher. And then the range of boiling is 180 versus 100 in Celsius. That gives you a scale. So this is the Celsius to Kelvin conversion. So whatever Kelvin number we have, we would take degrees Celsius plus 273.15. And so, for example, the human body temperature is 37 degrees Celsius. We convert this to Kelvin. We are going to take 37 plus 273.15. That's going to give us 310 Kelvin. We went ahead and rounded this down because the 0.15 is not going to be meaningful due to the 2 digits right here. We'll talk a bit more about that later, but you can already see it in effect. So let's talk about critical thinking and validity. You can test the validity of a claim by using what's called flares, or FLARES test. So the F stands for falsibility, the L for logical, the R for replicability. Excuse me, I ran out of water and I really needed more. The S is for the sufficiency. If a claim passes all 4 flares tests, then it may be true, though it can still be proven false. Remember, we can't actually prove anything true. This test is just to quickly try to make things that are false easier to tell that they're false. Okay? Is it going to be perfect? No. It's just going to be something that will help you get tricked less, which is very helpful, actually. If it fails even one of the tests, it's likely to be false, but not necessarily so. You would still want to test it if it's very important to know whether it's true or false. If it doesn't matter if it's true or false, because, like, I'm buying one of 3 products, I could use the flares test, and this mouse one has a totally incorrect way that they're saying this. It is definitely wrong. They're lying to me. Okay? Okay. Please let me know if you have any questions, if you would like anything else detailed in more detail. Yeah, let me know. I can always add extra videos talking about a specific topic or some more examples or use example problems from the homeworks, that sort of thing. You have a wonderful day, and your next video will probably be tomorrow because my voice is kind of giving up. It's getting kind of late. You have a wonderful night.